Hello and welcome to PCB Chat. I'm your host, Mike Buetow. Today's podcast is sponsored by PCB Update, the free digital newsletter for the printed circuit industry. Visit the website at pcbupdate.com to subscribe. I'm speaking today from Zuken Innovation World, the annual users conference sponsored by Zuken. I apologize for any background noise. In reporting, like electronics, sometimes you just have to innovate. I'm with Simon Freed of Nano Dimension, and Simon has just finished a presentation on additive manufacturing at Zuken Innovation World. Simon, in the past couple of weeks, Nano Dimension came out with what I would call a major development, which is that you have developed a process for being able to side mount components using your Dragonfly machine. Can you talk about that a little bit?
Absolutely. So what our goal is really to explore the ways in which additive manufacturing can deliver solutions to design or manufacturing challenges that are difficult to meet using traditional manufacturing processes in particular. And one of those issues is the notion of how do I deal with real estate constraints? Parts need to be small, but perhaps they need to have functions that limit the smallness that you can achieve. So there's an exploration there of how can I get that functionality without having to fall foul of that footprint that a traditional manufacturing process would require. One of the ways of doing that we've discussed in the past is embedding components within the board. That's one solution to that challenge. Another one that we announced a few weeks back was the opportunity to print capacitors into the board, again getting some real estate from that surface of the board to be used in different ways. And then the most recent announcement was using that additional real estate that is normally not tapped into to place components on the sides of the board. And so bringing those three opportunities together, each one of which is a challenge using traditional manufacturing, but relatively par for the course in an additive build-up process, allows you then to, in that instance, using traditional Gerber design, you can use pads and vias in such a way as to create contact points on the side of the PCB, allowing you then to solder those components. Perhaps give you a smooth surface on one side of the board. Perhaps you don't want components on one side of the board, but you need to have enough components to get the circuit to work, and you can't fit it all on one side. So it allows you then to essentially, assemble in an additional dimension, or at least on the sides that normally get overlooked.
What are the implications from a design point of view specific to their CAD tool? So, obviously you can take in data that is generated from some of the ECAD systems.
Yeah, so all of those instances, embedding is perhaps a different story because it requires a different approach to the design. But if you're looking at things like printed in capacitance, or this topic around using the side mounting, the design is done fully using totally traditional tools. So you can use a Gerber and Exelon output file format, and that's then something that allows you to design parts that have those sorts of features. So it's essentially using known entities like a via, but the via may be exposed on the edge. But that allows you then to use traditional design tools, not requiring any new technical know-how. It's just deploying what you currently do in places you might not normally think of using it.
So are the parts themselves, in this case, printed?
So the components on the announcement, absolutely not. So it's a traditional design. It's using additive manufacturing to create the bare board. The components themselves are completely standard components that are then soldered and mounted to the side of the board, exactly how you would if they were to be on the surface, on the upper surface, exactly how you would if they were to be on the upper surface. And you're then in a position to essentially treat it as if it was anywhere else. You do have to take counter for the fact that this is a very thin edge, and you may need to use some tweezers and grips when you assemble the thing in the instance where it's It's not an automated assembly process. Certainly not where we are, and not really an industry yet either.
Yeah, I haven't seen a placement machine yet that can, orient the board on its side. So,
precisely. Yeah. So that's something that is a challenge for the future. I mean, it's not necessarily something that we perceive as an impediment to the deployment of that kind of approach. If you look in the MID, the molded interconnect device space, there are certainly today automated assembly systems that are able to place components on the side, at angles, and underneath. So it's certainly well within the ability of current assembly systems to do that. But certainly I haven't seen any traditional chip shooters that are optimized for the 1.5 millimeters you've got on the side of your board.
And right now the technology is limited to capacitors?
So when it comes to printing in capacitance, yes. When it comes to the circumference of the board, there's really no reason that you wouldn't be able to place certainly resistors, capacitors. We certainly haven't attempted anything that would be a BGA on the side of the board, and various ICs would perhaps require some good thinking and a bit more prototyping
and
work.
Perhaps a very thick board.
And depending on exactly which one, you're then getting into sort of cube territory.
Sure.
But certainly if one imagines the way in which this type of technology would evolve, then certainly if you're trying to maximize functional density with available assemblable surface area, then I think that's a very valid point. Should the board be thicker but much smaller in X and Y, so that you could look at using different surfaces differently, there might be an advantage to having thickness over footprint.
So let's talk for a moment about creating capacitance through thin layers. Mm-hmm. Is this a similar process that was conceived by Zycon and later Sanmina, where they used a very thin layer to create capacitance? The patent expired several years ago at this point, but they were creating capacitance by using like 2 mil thin layers in the board. Is that sort of the similar idea here?
Fundamentally, it's the ability to interleaf very thin layers of dielectric and conductive material. Because of the additive process having really an extremely high resolution in the z-axis, the layers that can be printed can be exceptionally thin. So you're able to think in terms of microns rather than the maybe tens of microns that you might normally associate with a sort of PCB build-up. And so certainly the inspiration is to use the available materials as effectively as we can, and using that kind of an interleafing process opens up the opportunity to not just print in capacitance, but because it's printed, you are able to essentially customize the effect that you want, and the tolerances on those capacitors can actually be very, very high in terms of the performance of the part. Certainly on par with the sort of things that you'd find available in industry today. So it's a space saving approach to achieving performance that is equivalent and perhaps in some ways better, and certainly more practical from a tunability and optimization perspective than perhaps even using traditional components.
In your presentation today, you talked a bit about the challenge in overcoming additive technology, which is traditionally, or at least thought of as being more mechanical based, and getting into the electrical space.
Yeah.
Why don't you recap for our audience a little bit about how, and you can speak to Nano Dimension's particular tool, but how your system is trying to overcome some of the obstacles in designing for electrical, and how it interfaces with traditional ECAD tools.
Right. So certainly, the company's mission from the outset was to deliver to the electrical engineer the agility and workflow advantages that the mechanical world has adopted as a result of additive manufacturing. So if you look at teams of mechanical engineers and their workflows and how their day-to-day works and how they arrive at their end product, how quickly they can do that, it's been really transformed by additive manufacturing for the mechanical engineer. And additive manufacturing in the world of electronics will do exactly the same thing, and already does exactly the same thing for the electrical engineer. So the notion that you can design and then test from one day to the next allows a great deal more agility. It allows you basically to have an idea, to test an idea, but you're not constrained in the way, I think it's quite a conservative industry, precisely because the electrical engineer has an idea that prototype is going to cost. It's going to cost money. It's going to cost primarily time. And if you're in a space where time is highly valuable, it forces people to become more conservative. You don't want to take risks. If you have two ideas and one seems less risky, you're likely to go for the less risky one, even though it may not be the optimal design. It may require sacrifices, but you're doing it for reasons of caution. If one can de-risk and speed up the development process, what you find is that more prototyping takes place, more ideas get tested. The ones that appear riskier get a chance to actually be evaluated, and this is a process through that agile development process that gets you to a place where you have not just moved more quickly, but you've arrived at something that is more likely to be optimized for your particular set of requirements. So that is very much what's available from our system today. Folks will have an idea, they will print and assemble that part within a 24-hour period, and they will know what needs to be adjusted, or they might decide that they need to have a competition. Let's test 3 different boards this week, and we'll pick the one that works the best, fits the best, or has whatever performance advantages that one's looking for. So it allows you to test more quickly, but test more widely. And that's the first step, which is really allowing traditional manufacturing to pick up after this prototyping process happens. So you're designing in the tools you're familiar with, you're testing with an additive tool that makes it faster and less risky, and then you can transition to traditional manufacturing to scale up and reach those volumes. The second direction that additive is taking is by allowing people to explore what can be done with additive that cannot be done in any other way. And this is a very exciting space of applications that relate to the ability to create geometries, to use space differently, to look at traces as geometric patterns rather than horizontal and vertical images. So it's a different approach where you can start to see a merging of mechanical considerations with electrical considerations, with the ability to really cut down on the number of processes. System integration is a challenge, and with additive you can create complete modules that may contain within them all of the components or all of the constituent parts that you'd normally expect to be made from several assembled pieces. So you might need to have a battery and an antenna and a processor and have that fit in a particular space. All of those things can be delivered in one part, in one shot, in one design. And there you can achieve outcomes from a functionality perspective, but just practicality or even just comfort, from the perspective either of the designer or the end user. You have more options.
And I want to rewind for a moment, because when you're referring to testing, you're really talking about end product testing, not the circuit board testing.
Absolutely.
And it's a huge jump because if you can get away from a world where there's tens or hundreds or even thousands of vias, as you talked about in your presentation, then there's so many implications for time savings and cost savings. You don't have to plate the holes, you don't have to fill the holes, you don't have to test the holes. The circuits connect end to end with really no other noise or other things in between. Right. And this was one of the great things that I got around from your presentation. Maybe the most salient point is you get to the heart of what is a circuit. Right.
And it's a great question. Imagine if you have considerations of how close do different components have to be to one another. And today that would be a real challenge for the designer, because I've got my footprint and it's going to be not necessarily too easy to have those traces be where you'd ideally want them. But if you then open it up to a 3D interpretation, the degrees of freedom at the design stage are so much greater that you can come up with better answers for many of the challenges that are workarounds driven by traditional manufacturing. So you have the ability to position things where you really want them, and these are phenomenal advantages from a manufacturing process. You can go from 40, 50, 60 different steps to generally having one step of printing a part.
So one of the questions that came up in the presentation was the idea of using flex circuits and where the material science is headed in terms of having some flexibility or lack of rigidity, really, in the end product. Can you speak to that?
Certainly. I mean, we can all see how products are getting smaller, and the reliance on flex or rigid flex type circuitry is possibly it's the fastest growing part of the PCB market, really. And so there's clearly a need it speaks to the need for getting electronics into places that are tricky to get into. So whether you meet that by using additive to change the shape of your part, that's one way in which additive can solve that issue. The second one, of course, would be the wider your material set, and that can be from mechanical properties. You either want it to be very, very, very hard and very rigid, or you may want it to be bendable. Or if you look at a lot of the more traditional printed electronic space, there's a lot of excitement about stretchable as well. So flexibility, stretchability, that relationship between form and function are all different answers to that challenge of miniaturization or electronics everywhere, anywhere. So they're certainly, at the moment, when the materials we offer are primarily intended for use as a material for making rigid boards. There's a certain amount of flexibility that can be achieved in a prototyping environment if you perhaps need to have a sort of bend to fit, but that might be a one-time bend just to prove a point or just to test the part. To truly enable the engineer to work with what would perhaps in a traditional manufacturing context be a sort of a Kapton type, fully flexible material. Those materials are not something that we currently offer, and they're something that would be a material to be released in the future. We're not able to go on record when that will be, but the market is certainly clamoring for it. But at the moment, we're really focused on those rigid applications.
Great. Well, my guest today on PCB Chat has been Simon Freed, and Simon will be speaking at PCB West in September.
Absolutely.
Great.
We'll be there in September, yes.
All right, super. Well, thank you very much.
Thank you. Thanks, Mike.
I want to thank PCB Update, the sponsor of today's podcast. PCB Update is the free digital newsletter for the printed circuit industry. Subscribe at PCBupdate.com. This has been Mike Buetow for PCB Chat. Have a nice day.